And he joined Sano in something like 6 months ago. At the beginning, he was working in the teaming part at Cyfronet. Now he's employed by Sano Center, and he forms this part which is responsible for support for research, and it is this part of support which is related to elaboration of new computational methods, efficient computational methods. So, Tadeusz, floor is yours.
Yeah. Thanks, Marian, from introduction. So yeah, let's dive into the fascinating world of clustering and machine learning. So the short outline of my talk is that, yeah, first I will introduce shortly the clustering and what is it, and yeah, some properties of that. And then we will go through several examples from genetic expressions and genetic data clustering through data quality issues and improvement to image processing using clustering algorithms. So what is clustering? Yeah, at all. It's unsupervised machine learning algorithm or method for finding groups of similar objects in data. So it's unsupervised, so it means that we do not require any class labels a priori. So only on the data we want to find if there are some groups of objects we can say that are similar to each other. So what are the properties of clusters? So what we want to achieve. So now I will focus on the talk on the something called hard clustering, so that each point or sample belongs to only one cluster. There are also different types of clustering when it's not always the true, but now I will focus only on this aspect. And as the three clusters in this image are in circle, we see that within cluster we want the samples to be close to each other, so similar to each other, and between clusters we want that the samples are different. And just to be complete, what is the input data to the clustering algorithms? So one, it can be either the data matrix, so it's like classical tabular data input to machine learning algorithm, when the rows represent the objects or samples or patients or something like that, and in the columns we have the features or attributes of that object. So this is a rectangular matrix of n by p, and in order to use this kind of data in clustering algorithms, we also need to provide metrics. So it's kind of the algorithms know what does it mean that the point or the object is close to another object. And metric on its own is a big topic, and I won't cover it in this talk. And the second time of input data, it's possible to use something called the distance matrix, when from each pair of point there is the distance between this kind of point, this point, and by definition it's square. It has the size of numbers of object times number of object, and it's symmetric because the objects, the distances between objects are symmetric, and we can use then more flexible metric because we can use different weights on different features, or we can maybe use Euclidean metrics on some features and cosine metrics on other features, and then combine it, or even invent our OR way of saying what does it mean the objects are similar. And the applications of clusterings are kind of broad. We can in medicine use it to find groups of genes that have similar expression patterns, or we can identify groups in patients which have similar symptoms or have similar gene expression. We can use it to get subphenotypes in different diseases, and improve data quality by detecting outliers and filling missing data. So let's go to the first example, which is clustering of expression of gene expression using hierarchical clustering. So in this example, we have a panel of 60 human tumor cell lines from National Cancer Institute, and we have more than 1,500 probes or genes for expression patterns for the cell lines. And we want to find which cell lines are similar to each other according to this gene expression. And I use data from publication, which is in bibliography at the end. And algorithm I used is agglomerative clustering, when samples are compared using correlation. So if they have the similar correlation of expression, they are close to each other. And something called linkage, I use average. What is linkage and how does the algorithm work will be later. So as an output of this kind of algorithm, we get something called a dendrogram. So it's on the x-axis, we have each individual, let's say, sample, and in our case, it is one of the 60 cell expression cell lines. And on the y-axis, there is distance at which these samples are grouped. So we can say that if we then cut the dendrogram at some level, we obtain the desired number of clusters. And for example, in that case, we can see that the first cluster on the left mostly contains cell lines from melanoma cancer type. And for example, this cluster from from leukocytes, or and we can see that the cluster mostly responds to the cell lines, but it's not 100% clear situation. And there is also another way of visualizing this type of data. So it is using heat map. So this is like the raw data n by p, when we have individual samples, cell lines on the x-axis, and on the second axis we have the genes or probes, and this is only 100 from this 1,500 probes. And on this data, this kind of visualization, we can also plot how we could cluster the cell lines or patients in other cases with the how can we cluster the genes on the data, which genes have similar expression patterns and maybe are the same, used in the same pathways. And just by looking at the image, we can see that the let's say top part of the heat map has lighter colors than the bottom. So probably we can say that this is one cluster and this is other cluster. And if we want to look at the cell lines, we also can see that the other is the kind of red area here and the green area here. So probably there are two different clusters. And in fact, if we cut this, we will see that this is the first two clusters, and then we can create more cluster as we want. So here I used hierarchical clustering. So let's talk about what is this hierarchical clustering. So this is method of the connectivity family, and in general, hierarchical clustering can be either agglomerative or divisive. So it's either we start from the one element clusters and then merge them until we get one big cluster, or we start with one big cluster and then successively divide it to clusters of lower samples. As a result of this method, we obtain dendrogram. And big advantage of this method is that we don't need to specify number of clusters. We just get the data, run the algorithm, we get dendrogram, and then we can decide what we should do next. And also this algorithm is deterministic, and there is no randomness in the processing of the data and the data order. But we also need, as a parameter to this method, provide information how should we measure distance between clusters, because we have metric which specifies how individual objects are compared. But if the cluster contains more than one object, we need to say what is the distance between the clusters. And this is called linkage and will be described in following slides. So I will focus now on the agglomerative algorithm because I think it's more often used in the real world. And it's work like that. We start from one element clusters from each data point. So we have n clusters at the beginning. And then until we have more than one cluster, we select two closest clusters and then merge them. So this reduce number of clusters by one. And we are doing that until we receive only one cluster. So let's take let's take a look at the example of how the algorithms work step by step. And for that, I'm using a data set which contains global average cholesterol level in in couple of years, and it looks like that. There are uh, two groups, two clusters in the data on the scatter plot, and the first cluster contains data from men, and this upper from women. And because there is 40 something points here, I will use a smaller subset of data, only 8 elements, so it will be easier to follow the steps of the clustering. And I also display the distance between each point of sample. It's not as important to look at this now, but I only marked two specific distances. So the closest part of point, so is this between woman 2008 and woman 1998, which is 0.03, and the biggest distance is between man 2018 and woman 99. And it will become clear why I mark those 2 points in following slides. So let's start the algorithm. So first we get the we create the eight clusters, one of one element, and then we merge two closest clusters. And the closest cluster, the closest point was this woman 2008 and 1988, and it has the distance between those 2 points was 0.03. And if you look at the dendrogram, we merge these 2 points into one, and the line is at the point 0.03 approximately. And then we take another step. So we want to find another point which is in that case the closest to the existing clusters. So the next closest point is another woman 1988. So again we merge this to this two element cluster, and we have now 3 element clusters, and each remaining points are single elements. And we are going next. So next it looks like that those 2 points are most similar. So we merge them together, then extend it to another point. And then the distance between those 2 points is closer than between those 2 points. So we merge the women and create 4 element cluster. And finally we have this four element of the second cluster. And if we want to be precise and finish the algorithm when there is one cluster, we will merge those two clusters. And here is the data, and here is the resulting dendrogram. And you can see that this dendrogram ends about more than 1.1 because this is the distance between those 2 points. And here I use something called a single linkage. So this linkage is the way of saying how the clusters are similar. And there are a couple of used methods here. So in the example, I used single or nearest neighbor, which means that we take closest points between clusters. The other possible selections are complete when we take the most distant points, average, centroid, and word excitation. So yes, as a recap, for single excitation we take from compared clusters, we take minimum distance of each pair of points, and this is the resulting dendrogram as before. Now let's take a look what will happen when instead of taking the minimum distance, we will take the maximum distance. And what I want to emphasize here is that the order was that we first start with those 2 points, and then we added that line, so to create this this cluster. And when we start the complete linkage, so this farther distance, we start with the same step. But now, because if we want to calculate distance between the let's say the red line at this point, we will take the distance of this woman 88 to woman 2008, which is bigger than for this man to two men's point. So it's why the order of merging the points is different than for single linkage. So going next, we're adding more points, and things become interesting here when we have one 4-element cluster with all women's, and men's creates only 2 clusters. And previously we will merge those 2 clusters to create one. And now because the farthest distance is different from if we want to merge clusters, main clusters will need to take main 2018 and men 88, which is bigger than if we merge the main clusters with women. So in fact, here if we stop at 2 clusters, we will have different results. We will have bigger 6-element cluster, and this man will only take 2-element cluster. And as you can see, because the last connection of clusters was the highest distance of the point, and the highest distance in the distance matrix was 0.3, so the dendrogram ends on this 0.3. So let's take another example of linkage. This is average. So in that case, we calculate all possible combination between points in cluster and take average. And in that case, we will obtain this, let's say proper clustering of 2 clusters with 4 elements. And what I want to emphasize here that the next method gives also the same results, and the shape of the dendrogram is also the same, but the y-axis is different. And the next linkage I want to discuss is centroid linkage. So it's like for each cluster we take average 1 point to represent that cluster, and then we calculate distance between 2 points. So it's similar to previous one, but slightly different. But we also obtain this 2 men-women clusters. And last linkage, which is commonly used, the word linkage, is not using the distance as before, but it is based on variance. So the clusters are merged in that way that the increase of sum of square errors are minimal. And in that case also we have the same result, but if you compare the word and centroid linkage, you see that here let's say that the last connection is at much higher level. And if you want to compare different linkages on, let's say, artificial data set, we can see that if we use it for clusters which are more not so blobs, but more like arcs, only the single linkage is possible to discover that the shapes are more advanced than just simple blobs, and all other linkages like want to find the circular or elliptical shapes here. When we have 3 clusters which are clearly separable, each algorithm is working correctly. But when we have 3 clusters which have different variances, the single linkage will consider almost everything as one big cluster, and only the word linkage more or less gives the proper results. So as a summary of this hierarchical clustering, the advantages of this algorithm is that we don't need to give the number of clusters a priori, and using different linkage, we can obtain different results. For example, if you use the single linkage, we can obtain non-elliptical shapes, but this kind of method is noise sensitive. On the other hand, word linkage is better at noise resistance, but cannot discover these crazy shapes. complete and average distance are similar to each other, and I would say they are medium. And the last linkage centroid, I would say it's the worst of all of them, and it's probably the reason why it's not as not an option in scikit-learn to use this kind of method out of the box. So now let's focus on something different. So let's use clustering to improve the quality of data. In fact, to get the missing values. And for now, for why it's a problem at all? Because in medical data sets, the missing data often appears. And what can we do with this missing information? We can either remove entire sample, but we lose information which is not good in that case because the data sets can be small, or we can fill the missing data with some values, and usually it's mean values or median values across our whole feature, whole data set. But we can use clustering to improve this process. So we can split the data into clusters and then either use the mean or median, but just from the cluster, not from entire data set, or we can use more than one cluster and use distance to the centers of the cluster as kind of weight, so that the farther the cluster is, the less important and less impact it will have on the final value. And as an example, when I want to present this kind of data, I took the data from yesterday from Worldometers about coronavirus statistics, because we have so interesting times that coronavirus is everywhere. And let's say that we are interested in answering question, what is the total recovered and active cases in Spain? We don't have this data in the table. So let's say that we want to answer this question. So from the columns, and for the purpose of demonstration, I will use only two of them. So like number of deaths per 1 million and number of tests per 1 million. This is the scatter plot of the raw data. And by the way, it's interesting that some countries have more than 1 million tests per 1 million of population. So they are doing more tests than population. And for curiosity, I checked what are the countries. And this is Andorra, Gibraltar, Luxembourg, Monaco, and Iceland and Denmark are doing almost the number of tests as the number of population. But going back to the clustering, because the range of the data of the two features are order of magnitude different, because it's million and it's only 1,000. We need to scale the data, because the default metrics we will use is Euclidean metrics, which works well when the features have the same scale. So after scaling, we get this scatter plot on the right. And now we have to answer the question, what is the proper number of cluster here? This question will be answered in more detail in the next example. But just for now, there is a plot of kind of internal metrics of K-means algorithm with the number of K, and we want to select point which is kind of balance between the metric and the number of clusters. So that I would say that we should use 5 here. And on the right side is another metric of to assess how good a cluster. And here we are looking for the global or local maxima. And for that, I would say that we should use 4 clusters. So let's compare the results for 4 and 5 clusters on the same data. So if we use the global mean, we'll have 84,000 for total recovered and 111,000 for active cases. And this is the results of K-mean clustering of the data using 4 clusters. So we see that, there is one, let's say, green cluster here. These data points are split into half, more or less, and there is one cluster at the top. And for that clustering results, we will see that the Spain, according to the clustering, have much more active cases and slightly more the total recovered patients. But things are going interesting when we use 5 clusters, because now this point, so Spain is this bigger point, will be assessed to different cluster than before, and this is one new one element cluster. And for this 5 cluster results, the active cases are more or less the same, so slightly less, but it's the same range of value. But for the total recovered cases, we have only 15,000. So I would say in that case that we can assess that active cases are more than 200,000, but for total recovered, it's not so simple. And probably we should use more feature or different scaling or just different technique. And so this data imputation using k-means is sensible to the number of clusters. So now let's take a look how this k-means algorithms works. So this is representative of the centroid methods, or also it's called partitioning method in other sources. And the idea is that we have clusters, and each cluster has one representative. And for k-means, this representative is called centroid, and it's average over all features of the cluster. But to work for algorithm to be working, we need a priori the number of clusters. So this is the input parameter for that cluster, for that algorithm. And it works like that: we first initialize the desired number of centroids, of clusters, and then iteratively we are doing two steps. So we are looking for each point where is the closest centroid, so the closest cluster, and then we recalculate the cluster, so that is the mean of the all data points. And this algorithm we are doing until we converge to local optima, which causes some problems. But now take a look at the how it's working on this cholesterol example, like we did with hierarchical clustering. So let's suppose that we selected those 2 points of this initial cluster centroids. So in first iteration, we assign all the points to the right to this cluster, to this blue star, and this orange star will be one element cluster. And then we are recalculating the centroid. So this blue star is going much more to the right. But this will cause that the point here will now become closer to the this centroid than for that centroid. So we also reassign that and again recalculate the centroids. So this orange was moved to the midpoint of the line, and this blue moved also slightly to the right because there is 1 point less in the cluster. And there is another iteration because this point also changes now the cluster. So we reassign, recalculate, and it looks like this this solution is stable. So it's local minimum, and we obtained 2 clusters with different results than for hierarchical clustering. As I have said, the algorithms converges to local minimum, which causes sometimes a problem because depending on the initial starting points, we can obtain different results. So on the left is the results which was on the example, and SSQ is the internal metric, so it is some value, but we also can obtain using different initialization different result, which is also like local optimum, but with a higher sum of squared errors. And the usual way of solving this kind of problem with initialization is to run the algorithm multiple times and select the best options, let's say from 10 or 100 runs. But it's not solving the problem completely, it's just make it less important. For that example, although the the scale of the data is not as bigger as for the COVID, the scaling also should be applied. And in that case, we will also have only one stable solution, which is correct. So having said that initialization is important, let's talk how can we initialize the data. So the option one is just to randomly select the different desired number of points from the data set and then run clustering on that, this assign and recalculate steps. But it looks like there is better solution. It's called k-means plus, and it works on the assumption that if we spread the initial centroids over the entire space, we will get first better clusters, and second, the algorithm will converge to the optimal solution more quicker. So how the algorithm, this k-means initialization scheme works, is that we first select centroid as random point, and then calculate distance of each point to this first centroid, and select randomly, but the probability of the point to be selected as centroid is bigger if the point is more distant from the cluster. So we promote points which are more in other areas of the space. So then we have two clusters, two centroids, and then again we calculate distance to the closest centroid, and randomly select next point with probability proportional or just proportional to distance. And we are doing that until we have all k centroids generated, and then we perform the normal k-means algorithm, minimization algorithm. And because we are doing kind of random selections here, it also doesn't solve the problem of local optima, but it makes it less less important, and less. We don't need to take care of that as much. So let's also look at the same data set with different number of clusters to see what are the pros and cons of this k-means algorithm. So I would say that the only situation when the algorithm is working good is that when we have 3 clusters and we know we properly select the number of clusters, the cluster have similar variances and are circular in shape, because it's impossible for the algorithm to discover not elliptical shapes. And if the clusters have different variances, it also is not working properly. So to summarize this algorithm, the advantage of the algorithm and also disadvantage is that it's simple, maybe over too simple. We also need to know what is the number of clusters. So it's also the drawback of the algorithms, and it involves some kind of randomness. So we are not 100% sure that the solution we get is the best one. It is only possible to discover elliptical or circular clusters, and the cluster needs to have the say of similar variance. And as kind of maybe not a drawback, but just information, is that the central point of the cluster might not be the representative of the cluster. It may be like point which doesn't exist. And if we like to want that the point, in fact, the representative of the cluster, in fact, is one of the points, there are other methods from this family, so modification of that. So now let's use the same k-means algorithms and use it for image processing. So let's say that we want to compress image using the clustering algorithm. So for that, we can utilize the fact that each pixel can be treated as sample and the RGB components of the pixel as its features. And then if we select the proper number of colors and run k-means, we can replace the pixel with the centroid of this algorithm result. And yeah, and when we look at the example, this is from microscope imaging. The initial image has almost 7,000 colors, and when we compress select the k to be equal 4, we have like similar image, but we see that there are more details, and here are just flat color, which is so it is why I would say it's more like theoretical example, and it's not used in real applications. But some times ago, it was I think popular that that you can run clustering, k-means clustering with 2 clusters, and then treat the results as kind of segmentation. But now the methods for image processing are much more developed, so it's not as commonly used. But now in this example, I want to talk about how we should know what's the proper number of clusters. And unfortunately, there is no like objective method that we can say that in this data set there is that number of clusters. And we should use some knowledge we know about the problem, because maybe we are clustering patients' data and we might think that they are the healthy and unhealthy people, and maybe we know that they are 3 kinds of some disease, and we want model that. And one important information is that the clusters, when we obtain the cluster, we should be easy to interpret that this cluster is woman and this is woman, or something like that. And however, there is no one gold standard for that. There are some useful heuristic, and one of them is to use elbow method, or also named as knee method. And it's work like we plot the sum of squared errors of the k-means for different case, and then select the proper value. But sometimes it's no solution, because it's only heuristic. So let's talk what is the sum of squared distance. So it's the distance from each point to the center, to the cluster centroid, and it's like we square it and sum over all points. And it's also in different publications, books, and machine learning frameworks. It has different names. So it's sum of squared errors, or sum of squares, or sum of squared errors, or within sum of square distortion, and in sklearn it's named inertia. And internally, the k-means algorithm, this assigned reassigned steps, make this sum of square distance to minimize this value. Another metric for clusters is called silhouette score, and this is measure how well the clusters are separated from each other and how compact they are. And to compute the value for whole data set, we need to compute the silhouette score for 1 point, and this is the formula for that. So that's we take the mean value of distance to closest cluster, and also take into consideration the mean distance of points to points in the same cluster. And when we calculate this for all points and take average, we have the overall score over this clustering. So proper values, so the possible values from the silhouette score are in range from -1 to 1. So let's take a look at some example of that. So we see that if the clustering is good and we calculate the value for point which is properly clustered, the green distances will be small and the red will be big. And it means that in the perfect world, the A will be 0, so the score will be B over B, so B 1. So if the score is close to 1, it means that the point or the clustering is good. If the point is on the boundary of 2 clusters, the red and green distances will be same on average, so the score will be near 0. And in the last case, when we have wrong clustering, and this is kind of, I artificially made it that way, it's not the result of any algorithm. We clearly see that this blue point is wrong here. And in that case, the score is -1. So we want to look for cases when the silhouette score is as big as possible. And for example, for the data set with cholesterol men and women, when we plot the sum of square errors versus the number of clusters, so here we are using this elbow method. So we are trying to find the number of clusters in such a way that adding another cluster make not the gain of the adding new cluster is not important. So like, yeah, in that case, I would say it's maybe 4 or 5, something like that. And for silhouette score, we are looking for the maximum. So clearly for this data set, it should be 3. So let's look how this clustering, k-means clustering with 3 clusters look like. So it's on the right. And yeah, I would say it's compared to the 2-class clustering, it's much more interpretable, because we can say that the blue points are women, and the green are as men with high cholesterol, and the orange is men with low cholesterol. So I for sure this three-class clustering is better than this 2-class clustering. So now let's discuss another algorithm and another application, which is outlier detection. And again, why we care about that? For similar reason as for missing data, because it improves the data quality, and if we use then another classification or regression on the data set, we obtain better results. And detection using clustering is based on the assumption that the proper and normal cases are create big and dense clusters, and the outliers are somewhere at the out of these clusters. So for that, I took example from the publication about finding outliers in stroke clinical outcomes data. And there are 2 clinical parameters regarding the stroke. And there is the modified ranking scale, which is from 0 to 6, and 0 means that people is healthy, and 6 mean it's dead. And the second parameter is Bartle index, which is from range 0 to 100, and 100 means it's okay. And this is plot how this how is the relation between those two parameters. And the authors of the publication have tested this algorithm on Taiwan Stroke Registry, which has 100,000 points as a training samples, and as a validation and testing, they use National Institute of Neurological Disorders and Stroke datasets. And there were 4 different datasets, which in total has 10,000 points to compare. And then no, they are not using the original data, but they perform principal component analysis and use first 2 components, and they compared how 3 different algorithms for detecting a layer works. So they checked DB scan, hierarchical DB scan, and local outlier factor. And the results they obtained, they presented plots for each modified ranking scale. And the best algorithm from those 3 was the DB scan. And from the lowest achieved results for this algorithm was 92%, and the highest was 99%. And they are the appropriate plots for those, the worst and best cases. When the green point are the training data, the blue points are the properly discovered testing data, and the red points are the outliers. And I haven't said that, but they have all the points labeled as outlier or no, so it's why they can calculate the accuracy, because without that information, they cannot do that. And there is also another publication when they applied outlier detection using dbScan on whole as a part of the pipeline for classification patient for diabetes and hypertension. And yeah, as one of the steps is outlier elimination using dbScan. And they use 3 different data sets from diabetes, hypertension, and chronic kidney diseases. This is the sample of the sample result of the outlier detection. The circle points are outliers, and the red triangles are the correct points. And what's important here, they were able to compare the results if they run the random forest classification with outliers and after outlier elimination. So for the first data set, it's slightly removing outliers slightly make the results worse, but for the remaining 2, there was a significant improvement after outlier elimination, and average impact of this procedure is that it increases accuracy of the classification by 1.5%. So I think it's worth to do that. So what is the dbScan at all? dbScan is shortcut from density-based spatial clustering of application with noise, and this is example of the density methods, as the name suggests, and it works on the rule that the points where the high density of points in given region will create a cluster. And there are 2 important parameters for these algorithms. First is epsilon, or the radius of the neighborhood of a point. So, and the second is minimum number of points, and this is on the minimum number of points in the neighborhood of another point to be considered as core point. And there will be examples, so it will be much more clear, I think. And this also constitutes the minimum size of the cluster. And as the rule of thumb, the guideline is that either mean points should be double the number of features, or at least it should be 1 more than number of features. And there was the term core point. So now let's discuss what is this. So we say that the point is marked as core if within some distance, specified distance over these points, there are minimum number of samples. And the minimum number of samples includes this point also. So for the cholesterol example, with epsilon 0.3 and minimum number of points equals to 3. For example, this 1 point marked as red is core because it has within the radius at least 3 points. And this points at the top is also core point because it has even more than 3 points in his neighborhood. Another type of point is border point, and it's point which is not a core, so it has less than 3 points in his neighborhood, but it can be reached by, so it lies within some radius of another core point. And there are a couple of examples of core points in the data set, in this cholesterol data set. And lastly, we have something which is most interesting in that application, is that they are noise or outlier points, and these are the remaining which are not core nor border. And in this data set is only 1 point, which is it has no other points in his neighborhood. So the algorithm is quite complex, so I won't cover in much detail, but the generic idea is that at the beginning, we say that all points are unvisited, and then we select 1 point, and there are 2 possible options. The point is a core point, so it has enough neighbors So to create a cluster, in that case, we create the cluster from the point and its neighbors, and then we expand the cluster. So it's like we check if the newly added points also have enough neighbors, and if so, it's like the growing, the cluster grows, and yeah, at some point it stops because there is no more points to be added. And the second case is that the point we selected is not the core point, and we mark it as noise. And during later expansion of another point, it may be changed from noise to border or boundary. And then we just iterate this over. We cover all points. So this is the result on the cholesterol example. So if we want to describe shortly how the algorithm can work, is that let's say that we start from this point, and because this point has no enough neighbors to constitute a cluster, it will be first marked as noise. But then when we will consider this point, we will change. We will mark it as a core, change this point from noise to be border points, and add this two other points to cluster, and then we'll check the neighborhood of this point and this point, but there is no more points here. And similarly, we will do on the other side, and we will see that there is one noise point and two clusters. So I have said that there is some kind of guidelines how to select the minimum number of points to the algorithm, but it also looks like there is kind of heuristic. How can we select the epsilon for the algorithm? And it works that we calculate average distance to some number of nearest points, and we usually use the same number of as the mean points we will use for the final algorithm. And then from the average distances, we plot it sorted, and then again we use familiar elbow method to select the epsilon. So for this example, so this is the COVID example, I would say that the correct epsilon from three minimum points is between 0.1 and 0.2. And if I use 0.15, I will receive one big cluster, another cluster with countries which are doing about the same number of tests as population, and they will be 4 outlier points in this data set. And to compare how this algorithm behaves when we have different the epsilon, we can see that one of the benefits of the algorithm is that it's able to discover more complex shape and sizes of which are present in the data. If we use too big epsilon, we merge everything into one big cluster. And when we have clear separation and more or less good value for epsilon, we have correct clustering. But the drawback of this method is that it cannot be used or give wrong results when there are clusters with different variances. And it's because the algorithm assumes that epsilon, so that the radius of points, is the same for all clusters. And here, if we have clusters with different variance, we should use different neighborhoods for different cluster, which is impossible in that algorithm. So when we have too small too small radius, we will end up with having many small clusters. But when we have too big value, we merge everything into one big cluster and mark points as outliers. So there's big disadvantage of this method. And it's also worth to mention, maybe it's not big disadvantage. This advantage of this method, this algorithm, is that however the algorithm on its own is deterministic in the way it works, but the order of input points is important and points which are close to two clusters can be assigned to different clusters depending on the order of the points in the input data. Because Here is one example when we start from the left bottom. So we reach this point in the middle first, so it will be assigned to the blue cluster here. But when we run the algorithm on the same number of points, exactly the same values, but the order is inverse. So we will start from the upper right, and we reach this point, yeah, first from upper right, not from bottom left. So depending on the order, we have different, we can obtain different results. So as a big advantage of this algorithm is the ability to discover clusters of different shapes and sizes, and that we do not need to specify a priori the number of clusters. It will be like automatically determined, and it is somehow noise resistant. But if the clusters have different variance or density between them, the algorithm is not working properly. And also the results are sensitive to the order of points in the input data set. And last example is image segmentation using dbScan, because this algorithm was also used in that area of image processing. And authors of this publication have used the dbScan algorithm to detect lesion in dermatologist images. So the pipeline or the method they described is that from original image, they compute grayscale and then binarize it with some threshold. And so then we have the background and the lesion here. And then they have noticed, they have, let's say, invented, or the algorithm count boundary-driven dbScan, which is very similar to the dbScan I described previously. And the difference is that they noticed that the shape of the cluster can only be changed because of the change of these points at the boundary. So it's no need to check the points in the inside. So if they take a look at the point which is at the boundary, they check the radius as before, and if within this radius is enough number of points, this create a new polygon, and this polygon is merged to the cluster. So like they run with some random points and then create clusters. And again, this cluster is growing, and at some point it ends, and they have the lesion marked as some kind of shape. And they validated their algorithm on 50 images with annotated results from doctors. And for this, for the dbScan, they obtain 99% of precision and 78% of recall. And they also compute metric called border error, which is 6.6% in this case, in this algorithm. And they also compared this dbScan approach with other called active contours. And for the active contours approach, they have the same border error, but dbScan has less variance. So it's like the better algorithm from those two according to their results. So as a kind of summary, the clustering can be used in many different areas in medicine. And I would say that more versatile algorithm is hierarchical clustering, because it can be used for grouping genes, patients, for clustering RNA-seq data, for imputation of data, and it also has been applied in subphenotyping depression disease. The next important algorithm, I would say, is dbScan, because the most often used as outlier detector, but also this more clever application on images are also possible. And like the less important is the k-means, because it's overly simple for practical applications. And it's also worth mentioning that that's not the all algorithms that I present in medicine and in clustering at all. For example, there is algorithm called latent class analysis, which is used for subphenotyping diseases, which is important, for example, in autoimmunological diseases, when we can discover subphenotypes which can be treated in different way. And it's also one of the topic we are working at Sano. This is some kind of resources I was using to present this presentation. And it's all from my side. So thank you.
Thank you very much, Tadeusz. Thank you very much for this nice overview of all these clustering methods.